Hi, welcome to this new video of Math-S400, Mathematics and Economic Modeling. In this video, we're going to continue with Brouwer's fixed point theorem. In particular, we're going to see at least an outline of the proof of this theorem for some cases. Okay. So let's recall what Brouwer fixed point theorem actually said. So if we have a subset S of Rk, and we assume that S is convex and compact, and we already give some indication that this convexity is actually a bit too strict. But anyway, so we have a function S from S to S, which is continuous. Well, if these conditions are satisfied, then we've said that there exists a vector x and S such that f of x is equal to x. Okay, so there's the function f has a fixed point. So here we're going to have a look at the proof of Brouwer's fixed point theorem, and in particular we're going to look at cases where S is what we call an n-dimensional unit simplex. Okay, in the last lecture on Sperner's lemma, I already explained to you what a one-dimensional, two-dimensional, three-dimensional simplex is. Now this is a special kind of simplex, it's namely the unit simplex. Okay, so let me first give a definition of what this is. So the n-dimensional unit simplex, we're going to use the notation delta n to denote this. So what's the n-dimensional unit simplex? Well, it's the set of vectors x in Rn plus 1 plus, okay, so it's a vector which consists of components x1 until xn plus 1, right? So it has n plus 1 terms, and with the property that if we add all these numbers together, all the components of x together, we get a number 1. Okay, this is where the name unit comes from. Okay, so delta n contains vectors that are of dimension n plus 1. Okay, and it will become clear why this is the case. So let's first have a look at delta 1 as a case, special case. So these are the vectors x and R2, right? So there's component x1 and there's a component x2. So these are in R2 plus. So what do we know about these vectors? Well, if we add up x1 plus x2, well, we get the number 1. Okay, so if we draw this two dimensions, so here we can plot x1, here we can plot the second component. So if x1 is equal to 0, then x2 is equal to 1. Okay, so this point should be under. If x2 is equal to 0, then x1 is equal to 1. So this point should also be in there, and then delta 1 contains all the convex combinations of these two points. So basically it's this line here, right, with this endpoint and this endpoint. So if I turn my page and if I forget about the axis for a minute, what I have here is just a line segment. Okay, and we have seen that line segment is a one-dimensional simplex. So this can actually be seen as a one-dimensional simplex. Okay, where here I have this point which is the vector 1, 0, and here I have the point which is the vector 0, 1, and then all the points on the simplex are all the numbers, all the vectors x1, x2, which were non-negative, and the components add up to 1, right? So this is where the one-dimensional simplex comes from. We can, for example, we can also have a look at delta 2. These are now vectors that consist of 3 components, x1, x2, x3, so there are elements in R3 plus. And if we add up these 3 numbers, they have to add up to 1. Okay, so if we draw this in a 3D diagram, okay, I'll do my best. So here we have x1, x2, and then x3. So if x2, x3 are equal to 0, then x1 has to be equal to 1, right? So this point is on the simplex, this point will also be on the simplex, and then this point will be on the simplex. So if you look at all the convex combinations of these points, what we end up with is this surface here, which is a triangle, and you have seen that a triangle is indeed a two-dimensional simplex. Okay. So this point now corresponds to the vector 1, 0, 0. This point is this point 0, 1, 0, and here we have 0, 0, 1. Okay, so what are we going to do? We're going to use this n-dimensional unit simplex, and basically we're going to show that Brouwer's theorem holds for delta n. Okay, now this is a subset of Rk plus 1, Rn plus 1. Okay, you have seen that a function from this set to this set, which is continuous, will have a fixed point. Okay, so why do we only need to show it for the simplices? Well, remember from last lecture I showed that if you have a set T, which is like this, and then we have some other set S, and if there's a continuous mapping from T to S, G, which also has an inverse, G minus 1, okay, so there's a bijection G from T to S, which is continuous. Okay, so this one is continuous and the inverse is continuous. Then any continuous function here on S will have a fixed point as long as a continuous function on T will also have a fixed point. Okay, so in order for a continuous function on S to have a fixed point, well, it suffices for any continuous function on T to have a fixed point. Okay, so what I want to say is, in order to show that if you have a continuous function on the set, then this function will have a fixed point, it suffices to find such a set T that has this one-to-one mapping from T to S, and such that any continuous function on T has a fixed point. Okay, so what are we going to do? Well, for T, we're going to take our n-dimensional simplex, and then if you can show that any continuous function on this n-dimensional simplex has a fixed point, well, then we can use, or we can deform the set in a continuous way to another set, and then any continuous function on this other set will also have a fixed point. Okay, so basically we can restrict our domain where we prove Brouwer's 6-point theorem to these n-dimensional unit simplices. Okay. So for the proof, what I'm going to do is I'm going to prove Brouwer's 6-point theorem first for this one-dimensional simplex. Okay, and then I will use a very similar proof, basically the same proof, but with a little bit more flesh. I'm going to also prove it for the two-dimensional simplex. Okay, I will not consider the general case because in these two cases I can still make some pictures, and I think it will be obvious how to generalize it to more than 2 dimensions once you have seen these two. Okay, so for the case 1, what we have, so we consider a function from the one-dimensional unit simplex to the one-dimensional unit simplex, and we assume that f is continuous. Okay, and you would like to show that there exists an x in delta 1 such that f of x is equal to x. Okay. So in order to prove this, we're going to make use of Sperner's lemma. So remember that delta 1 was equal to this picture, right? This line segment here that went from 0, 1 to from 1, 0 to 0, 1. Okay, and let me draw this picture here again, make it a little bit bigger, like this. So this is the point 0, 1, and this is the point 1, 0. Okay, and the proof that I will use is a proof by contradiction. Okay, so what I'm going to do, I'm going to assume that for every x in delta 1, f of x is different from x. So assume for all x in delta 1, f of x is different from x. So let's have a look at a particular x, right? So x is in delta 1. So remember, delta 1 was all the set of vectors, was this set here. So it's all the set of vectors in R2 plus, such that the two components sum to 1. Okay, so particular x is in R2. So x has arguments x1 and x2. Okay, and now let's have a look at f of x. So f of x is also in delta 1, right? Because the function maps some point on this line and it maps it to some other point on the line. Okay, so f of x is also in delta 1. So for example, we can set it equal to the vector y, and then y will also be equal, have two components, so y1 and y2. So instead of y1 and y2 and equating this every time, I will use shorthand notation. So the first component of f of x, I will call this f of x, and then with the subscript 1. Okay, and the second component I will denote this by f of x, but then with the subscript 2. Okay, so these are the same vectors, right? So if f of x is equal to the vector y, then the first component of y is denoted by this, and the second component is denoted by this. So fx subscript 1 is the first component of the vector fx. Okay, so these are numbers, right? These are two numbers, and these are two numbers. This is a vector. Okay. So what does this say? We assume that for every x in delta 1, this vector is different from this vector. Okay, x is different from f of x. So consider a subdivision of this line segment, right? So every node here corresponds to a node on this line here, right? So basically these are all vectors of dimension 2, right, whose components add up to 1. So we're going to invoke Sperner's lemma at some point. So in particular, we're going to color the vertices on this line segment. And we're going to use two colors. Okay, I have here two colors, red and green. So I prepared myself for coloring vertices. Okay, so and in particular, okay, so what are we going to do? So if we're going to compare this vector here, fx1 and fx2, with the vector x1 and x2. And in particular, if fx1, so the first component of f of x, if this is smaller than the first component of x, we are going to color the vertex red. In particular, color the vertex x in red. Okay, and then if f of x1 is greater than x1, okay, so this means that it's not red. And if f of x2 is strictly smaller than x2, then color x in green. Okay, so this is the rule that we're going to follow in order to color these vertices. So my claim is now that this is a coloring that is corresponds or that's allowed for Sperner's lemma. So recall, and for Sperner's lemma, what we needed is that first of all, every vertex has a color, right? It's either red or green. It's impossible that we cannot assign a color to this. And second, this color here should be different from this color here, right? So the vertex 0, 1 should have a different color than the vertex 1, 0. So let's check both of these things. So my claim is, first, my claim is that every vertex x has a color. Okay. So we're going to use an argument by contradiction. So assume not, right? So assume that we have x has no color. So what would happen then? Well, if x has no color, then it's not red, right? So this means that this is not true. So in other words, f of x1 is greater or equal to x1. Okay, that's the first thing that we can say. Also, we know that it's not green, right? Because if it doesn't have color, then it's not red and not green. So we already know that this is not true, right? So f of x1 is greater or equal to f of x1 is greater or equal to x1. But it's not green, so we know that this has to be false, right? Because this isn't this green. If this holds and this holds, we know that this holds, right? This is because it's not red, so this has to be false, right? So we have that f of x2 is also greater than x2. Now x1 and x2 are the vector x, and f of x1 and f of x2 are the vector f of x. And we know that x is in delta 1, right? And f of x is also in delta 1 because f goes from delta 1 to delta 1. So we know that if we add up x1 and x2, then we get the number 1. Okay. Also, if we add up these two numbers, we also get 1. So what do we have here? We have two non-negative numbers. Here also two non-negative numbers. These are both bigger than these, or greater or equal to these, and they have to sum to the same number. Now, if one of these inequalities would be a strict inequality, then of course this sum here would be strictly bigger than this sum here. Okay. Now, given that the sums are equal, this means that both of these inequalities have to be equalities. Okay. Need to be equalities. Or in other words, I have that this vector has to be equal to this vector, or f of x is equal to x. If f of x is equal to x, then of course by definition x is a fixed point. However, we started by the assumption that there is no fixed point. Okay, so this contradicts the fact that there's no fixed point. So this argument here has to be false, right? So the assumption that x has no color has to be false. So indeed, every vertex needs to have a color. Okay. If some vertex doesn't have a color, then it's a fixed point. We assume there's no fixed point, so every vertex needs to have a color. Okay, so in particular, we can color every point here on this line. Okay. So the second condition that we needed to show is that this color is different from the color that we have here. So let's have a look at the color. So what is the color of the vector 0, 1? That's a good question. Okay, so we have the vector x, which is 0, 1. And now we have to look at the mapping f of the vector f of x. So this is fx1 and fx2. And again, these add up to 1 and these add up to 1, right? Because both of them are in... This, of course, adds up to 1, and this has to add up to 1 because it's in delta 1. Now, this here, my claim is that this cannot be equal to 0, okay? Because if this first component is equal to 0, and then these two have to add up to 1, then the second here has to be equal to 1. Okay, so if this one is equal to 0, then this is equal to 1, and then these two are equal to each other. And if these two are equal to each other, then again we have a fixed point, which contradicts the assumption that there was no fixed point. Okay, so this here, f of x1 is different from 0. Okay, so if f of x1 is different than 0, then it has to be strictly bigger than 0, right? Because f of x1 is between 0 and 1, right? Because it's non-negative and it has to add up to 1 here. So if this is different from 0, then f of x1 is bigger than 0. So here we have a strict inequality between this and this. Okay. And then, of course, because they have to add up to 1, we have a inequality here. So in particular, we have f of x1 is bigger than 0. So we are in this case here, and f of x2 is strictly smaller than the second component of x. So f of x2 is strictly smaller than f of x. So this means that this one here has the color green. Okay, so 0, 1, we can color this in the color green. All right. I don't know if you can see it, but this is green. Okay, and then what's the color of 1, 0? Well, we can use a similar argument, right? So let's take 1, 0, and then f of x, which is f of x1 and f of x2. Of course, these have to add up to 1, these have to add up to 1. So we can use a similar reasoning here. If f of x2, if this would be equal to 0, and this would be equal to 1, because they have to add up to 1, then these two vectors should be the same. However, they cannot be the same because we don't have a fixed point by assumption. Okay, so we have that a strict inequality here, and then because they have to add up to 1, we have a strict inequality here. So f of x1 is smaller than x1, so this has the color red. Okay, so this is in red, so I'm going to color red here. And then, as you already have seen from point 1, every other vertex either is red, okay, or is green. But at least we can color it. Okay. So these two rules tell me that the coloring is okay to use Sperner's lemma. So if you apply Sperner's lemma, capital letter, well, then we know that there is at least one small segment with two different colors. Okay, so for example, I had that this was green and this was red. For example, here I have reds and here I have two greens. So maybe it's good to see what's the intuition behind this here. Okay, so we had that this was 0, 1, and this was 1, 0. So if the first component decreases, we go here over the line, right? And if this first component increases, we go in this direction. So if the first component decreases, then we're in red. So this actually means that if you look at the mapping F for these points, then for all the red points, F goes to the left of this point, right? So here also if I look at the mapping of this point, I will be somewhere on the left. Here I will be somewhere on the left. Here I will be somewhere on the left. And for all the green points, my mapping will take me somewhere to the right of this point, right? So basically you look at if F is to the right, you color it green. If F of this point is to the left, you're going to color it red. Okay, so that's the intuition behind this coloring that you get here. Okay, anyway, so we have an interval which is red-green somewhere in the graph. I could take this one, or I could this one. We know that, or this one, there's an odd number of them, so there's at least one. Okay, so there's at least one small segment with 2 different colors. So what I'm going to do, I'm going to select one of them. For example, this one here. And let me call the green vertex, let me call this G1. Now 1 is not a component of the vertex, but it's just the number that I will use. And let me call the red vertex, let me call this R1. Okay. So what I can do now is I can, for example, divide all the intervals into 1/2. Okay. Now I have a smaller subdivision of this interval. Okay, and then again, for all the vertices that were not colored yet, I can give them a color. For example, this one is red, and this one is red, and this one is red. This one might be green, and this one might be green, and this one might be green. Okay, so now I have a smaller subdivision, and again, I can use Sperner's lemma. These two colors are different. Everything can be colored using the same arguments I have done before, and I can again find a red-green, smaller, now tinier interval. For example, this one and this one here. So let me call this the vector G2. Let me call this the vector R2, right? So the red one is the R and the green one is the G. And I can do this over and over again, right? Each time I can take more points within all these intervals, and I can look at a smaller subdivision, and each time I can find a smaller and smaller interval. So I can take smaller and smaller subdivisions. Okay, each time I can find an interval with 2 different colors. Okay, so you see that this interval was first here and then here, so they can move around on the line, right? We don't require them to be close to each other or anything. We just only require them that this was first a bigger interval, and now we have a smaller one, right? So each time you will have a smaller and smaller interval. And the colors at both ends of these intervals are different. So call red vertex Rn, right? So this is for the end subdivision, right? So this was the first subdivision, then I took smaller intervals, so I have a second subdivision, then I took smaller intervals, then I have a third subdivision, and so on. So for the end subdivision, I have a red vertex Rn and a green vertex Gn. Okay, so each time I can do this, I can find a red one and I can find a green one. Okay, so my red vertex Rn is a 2-dimensional vector, right? So it consists of two components, and let me call the first component Rn1 and Rn2. Okay, so n is refers to the subdivision, and 1 and 2 refer to the components. And then of course I have Frn. Okay, so these also consist of two components, namely Frn1 and Frn2. And I know that R is red. So in particular, f of x1 is smaller than x1. Okay, so I have that f of x, f of Rn1 is smaller than Rn1. Okay, and I have the same or similar thing with the green vertices. So Gn1 and Gn2, I can look at the mapping f of Gn, f of Gn1 the first component, and f of Gn2 the second component. And now for this vertex is green, so I know that f of 2 is smaller than x of 2, or in particular f of Gn2 is smaller than Gn2. Okay. So what do we also know? Well, we know that these subdivisions get smaller and smaller and smaller, right? So in particular, we can each time take the midpoint between every interval. So basically, the size halves each time we take a smaller and smaller subdivision. So if you would look at the distance between the vector Rn and the vector Gn, well, if n goes to infinity, well, this would converge to 0. Okay. However, if we look at the sequence Rn, and if you look at the sequence Gn, well, they wander around in this interval, right? And it's not because this goes to 0 that these sequences also go to 0. They tend to get closer and closer together over time, but it's not like we are sure that they have to converge to some vector in this interval. Okay. Now here is again the magic of the Bolzano-Weierstrass theorem. Why? Because, well, we know that delta 1 is a one-dimensional simplex, right? And this is just an interval. In particular, it's this line segment here. And we know that line segment, you can see that it's bounded and it's closed. So it's compact. So by the Bolzano-Weierstrass, because these vectors live in a compact set, then there is a convergent subsequence. Okay, and in particular, we can take these subsequences to be at the same indices, right? So for example, if R10 is the first element of the subsequence of R, then we can take G10 to be the first element of the subsequence of G. So in particular, what we can do is we can take a convergent subsequence of R, then restrict G to this subsequence, similar as what we had done for the Bolzano-Weierstrass theorem for the k-dimensional case, if you remember. So we take a convergent subsequence of R, restrict G to this subsequence, and then take a convergent subsequence of this subsequence of G, right? And then both, if I restrict R to this subsequence of G, then both R and G will converge along this subsequence. Okay, so without going into too much details, well, we know that there exists a subsequence R phi n that converges, for example, to R, and there exists a sequence G phi n that converges, for example, to G. Okay, so these are now these subsequences of this one and this one. Okay, so if I look at the distance between R and G, well, this is equal to the distance between R and R phi n plus R phi n minus g phi n plus g phi n minus g. Okay, so this is the simple trick that we used over and over again in previous lectures, the triangle inequality. So this is r minus r phi n plus r phi n minus g phi n plus g phi n minus g. This here converges to 0, right, because of this. This here, well, you know that this interval gets smaller and smaller, so it also has to converge to 0 along a subsequence. Okay, so also here this has to converge to 0, and then g phi n converges to g. So all of these things converge to 0, so this will be smaller than any number that I can think of, right? So a number that's smaller than any strictly positive number or any non-negative number that I can think of, then it has to be equal to 0. So this means that r is equal to g, right? So in particular, r phi n converges to r, g phi n converges to g. These two sequences get closer and closer to each other, so these two limits have to be the same, right? That's the intuition behind this derivation. So these are equal, so let's call this vector y. Okay. In order not to make it green or red, let's call it y. Okay. Good. So let's have a look at this vector y. So the r phi n's are red. Okay, and we know that for all the red this inequality holds. All right, so in particular, r phi n, the first component, is bigger than f of r phi n, the first component. The g phi n's are green, so g phi n, the second component, is greater than f of g phi n, the second component. Okay, these are the inequalities because this is red, right? We colored it in red, and this is green. It has the green color. So now let's take the limit for n going to infinity. So r phi n converges to y here, right? So the first component of this vector has to converge to the first component of this vector. So this converges to the first component of y. Okay, so this vector here is y1, y2. So this converges to y1. R phi n converges to y, and f is continuous. So f of r phi n converges to f of y. And then the first component of this limit, this first component of course has to converge to this first component. And every term here is strictly bigger than every term here, so in the limits I will keep my inequality, but it might change to a weak inequality. Okay, so strict inequalities in the limit may turn into weak inequalities, but they cannot change the inequality. This cannot be strictly less than. I can do a similar thing here. If I take the limit of g phi n2, I get g, the g phi n's converge to y, so I get the second component of my y. And here, because f is continuous, I get f of y, but now the second component, and the inequality is like this. Okay, so this here and this here, this is the continuity of f. This is where we use continuity. Okay, so far we haven't used continuity at any point, but this is really why we need it. So we have a vector y. The first component is greater or equal to f of y1, and the second component is greater or equal to f of y2. 2. Okay, so this is my vector y, and this is my vector fy. Now the domain is compact, right? This means that y, which is the limit of these r's, will also be in delta 1. Okay, so if I add them up, they have to add up to 1. F is continuous, so if I take a sequence, this sequence of f's lives in delta 1, so the limit also has to be in delta 1, so also here these add up to 1. So again, I have two non-negative numbers, they add up to 1. Here two non-negative numbers, they add up to 1. This is greater or equal to this is greater or equal to this. I cannot have a strict inequality here, otherwise this would be strictly bigger than this one, okay, which is not the case. We have equality here. So this means that both of these have to be in equality. In particular, the vector y should be equal to the vector f of y, which means that y is a fixed point. And this is indeed a problem, because we started by assuming that there is no fixed point. Okay, and then the limit we have found a fixed point, so this is the desired contradiction, which finishes the proof, at least for a function from delta 1 to delta 1. Okay, so let's recap. We had delta 1 was a one-dimensional simplex, so we can depict it like this. We have chosen a coloring based on whether the first component of the f of x is smaller than x1, the first component of x, or whether the second component of f is smaller than the second component of x. Then we have used a couple of arguments, right, to show that indeed every point can be colored, otherwise you would have a fixed point. And second, that also this point and this point have different colors, right? So basically, if we look at f of this point here, it has to go to the right, and f of this point has to go to the left, right? This is why they have different colors. So we invoked Sperner's lemma, and we have found that there's at least one small interval with two different colors. And then we use the limiting argument. So in particular, we use the smaller and smaller subdivision of this simplex into smaller and smaller segments. Each time we can find an interval with two different colors, and we called at the end iteration, we called R in the red vertex and G in the green vertex of this interval. Okay. And then because these intervals go to 0, the distance between the red and the green one goes to 0. These are sequences in a compact domain, so we can find a convergent subsequence. This uses the Bolzano-Weierstrass theorem. And then, using some limiting argument, we have shown that the limit of these vectors have to be, in fact, a fixed point of this, right? So the idea is that the limiting point has to be both green and red, and if it's both green and red, well, this is the definition of a fixed point. Well, it's actually not green and red, because for green and red we have strict inequalities, right? But basically that's the idea that you get so close to each other that you cannot move away anymore to the left or to the right, so you will have a fixed point. And this is in contradiction with what we assumed, that there was no fixed point. So in the rest of this lecture, what I'm going to do is I'm going to basically do the same proof again, in order to make that you understand right, but I'm not going to use delta 1, but I'm going to use delta 2, right, one dimension higher. Okay, so let's go to the Brouwer 6-point theorem, but now we're going to look at functions from the two-dimensional unit simplex to the two-dimensional unit simplex. Okay, so remember, the two-dimensional unit simplex was a set of vectors x1, x2, x3. So now you're having 3 dimensions in R3+, such that x1 plus x2 plus x3 is equal to 1. Okay, and if you remember the picture, you had the three-dimensional axis, so you had this point, and this point, 1, 1, 1, and basically you have to make this triangle here. This is the two-dimensional simplex, two-dimensional unit simplex. Okay, and we assume that f is continuous. Okay, and now you have to show that there exists some vector x in delta 2 such that f of x is equal to x. Okay, so the proof is going to be very analogous to the proof for delta 1, but with some special cases in order to make sure that the coloring also works in this case. Okay, so as the proof in the previous part, we're going to assume the proof is going to be by contradiction. So assume that for all x in delta 2, f of x is different from x. Okay, so let me redraw the simplex here in order to make it more clear. So we have 3 corner points. This corner point, let me take this to be the x-axis, so this is 1, 0, 0. If this is the y-axis, then I have 0, 1, 0, and then this is this point here on the z-axis, so this is 0, 0, 1. Okay, so as before, I can divide this simplex into smaller triangles. Okay, like this, and then a triangle here, and a triangle there, triangle here, and so on. So similar to the interval, I can make these triangles as small as possible, right, by keeping on adding triangles to this picture. Each time I can halve all these segments here and then construct smaller and smaller and smaller triangles. Okay, so in the limit, the distance between any two vertices of a small triangle will also go to 0. Okay, so this is how it's going to generalize in the end. So I need a coloring. So in this case, I need 3 colors. So I'm going to use these 3 colors. So red, green, blue, and I'm going to color these vectors, right? So these are vectors in 3D, right? They're on this triangle here. I'm going to use, as before, the value of the vector x and the value of the vector f of x. And now these consist of 3 numbers, x1, x2, x3, and f of x consists of f of x1, f of x2, and f of x3. Okay, and I'm going to compare these two numbers, and these two numbers, and this will determine my colors. Okay, so let me put my colors here. So in particular, if so my rule is the following: if f of x1 is smaller than x1, okay, this is similar. I'm going to color the vertex x in red. If f of x1 is greater or equal to x1 and f of x2 is smaller than x2, well, then I'm going to color x in green, let's say. And then for my third color, well, if it's not red or green, right, which means that f of x1 is greater or equal to x1 and f of x2 is greater or equal to x2, And now f of x3 is smaller than x3, or then color x in blue. Okay, so these are the rules to color. So this is rule number 1, this is the rule for green, and this is the rule for red. Okay, and you can see quite easily that no vertex can have more than one color, right? Because if it's not red, if this is the case, then it cannot be red, right? So this is not red, and at least it's not green, right? So they cannot, it's impossible that the vertex has the same colors, right? So this is something that actually we also needed to check, but I hope it's clear from the rules that this is obvious. So we would like to color these vectors or vertices, right? So remember, for a Sperner's lemma to hold, what we need is 3 things. We need to be able to color every vertex, right? Everything needs to have a color. That's one. Second, these 3 corner vertices need to have different colors. And then any vertex on this line here, on this boundary, needs to be have either the color of this one or the color of this one. Every vertex on this boundary here needs to have the color of this one or the color of this one. And every vertex here on the boundary needs to be colored like this vertex or like this vertex. Okay, so these are the 3 things that we need to make sure that they're also valid for this if you choose this coloring. So let's first show that every vertex has a color. Every x has a color. Okay, so we have x1, x2, x3, which is our vector x, and then we have the vector f of x, which is fx1, fx2, and fx3. So you have to show that every x has a color, so the proof is going to be similar as what we have done for the one-dimensional case. So we're going to use an argument by contradiction, so assume x has no color, right? So assume that we have a node here, x, one of these, and it doesn't have a color. Okay, so what do we know then? Well, we know it's not red. Well, if it's not red, then this condition cannot hold, right? So f of x1 has to be greater or equal to x1. So we know it satisfies this condition, but it's not green, so it has to violate this condition, right? So f of x2 has to be greater or equal to x2. Then satisfy this condition and satisfy this condition, but it cannot be blue, so f of x3 has to be greater or equal to x3. All these both vertices are in delta 2, so the elements add up to 1. Okay, so I can add these up. I get 1. So here I get 3 non-negative numbers, here I get 3 non-negative numbers. This one is greater or equal to this one greater or equal to this one greater or equal to this one, and they add up to both 1. So none of these weak inequalities can be strict, because if they would be strict, then this number should be strictly bigger than this number, right? It's a similar argument as before. So from this, it follows that all these weak inequalities are actually equalities. So it follows that x is equal to f of x. So x is a fixed point, and this is a contradiction because we assume that there is no fixed point. Okay, so this claim here that x has no color has to be false. Okay, so every x has a color. This shows this theorem. Okay. Next, we have to show that these 3 points have different colors. Okay, so let's first look at this point here, 1, 0, 0. So what is the color of 1, 0, 0. So here we have x, which is 1, 0, 0. Here we have f of x consists of fx1, fx2, fx. And we know that they add up to 1 and these add up to 1. So let me first show that f of x1 cannot be equal to 1. So what would happen if f of x1 is equal to 1? Well then, because these three numbers add up to 1 and they're all non-negative, this has to be equal to 0 and this has to be equal to 0. Right? So we get the vector 1, 0, 0, which is equal to 1, 0, 0. So this would mean that x would be a fixed point. And we started from the assumption that there is no fixed point. Okay, so this means that this number here has to be strictly smaller than this number here. If f of x1 is strictly smaller than 1, well, then we know that this vertex is red. Okay, so this vertex has to be red. So we can already color this one here. Is going to be a red one. So let's now look at 0, 1, 0. You can use a similar argument, 0, 1, 0. So 0, 1, 0. fx1, fx2, fx3. Add up to 1 both. So again, this second component cannot be equal to 1, because if fx2 is equal to 1, then the top and the bottom element has to be equal to 0, and you get this vector 0, 1, 0, which is equal to this one, which would mean that this x would be a fixed point. Okay. So we need that this one is strictly smaller than this one. Of course, f of x1 is always greater or equal to 0, right? Because the components are non-negative. So we have f of x1 is greater or equal to 1, and f of x2 is strictly smaller than x2. So we know that this one has to be green. Okay, so this node here is green. And then you can do a similar thing. It's almost completely analogous. So I will, so this is blue. Everything is blue, but this is also blue. You can show that this 001 is a blue node, right? You can use a similar argument as the two that you already have done before. So maybe it's a good exercise to do this for yourself. Okay, so far we have shown that every vertex has a color, and we have shown that these three vertices have three different colors. So now we have to show, for example, what shall we do? For example, we have to show that all the vertices here, these three ones, are blue or green. Okay, so let's do this. Let's take a vector here. So this, I think this is point number 3. Yes. Take a vertex on the side from, so this is a side from 0, 1, 0 to 0, 0, 1, 0, 1, 0 to 0, 0, 1. Okay, so what do we know about this vertex? Well, this is a point on this line, right? And this is all the points that are a convex combination of this vector and this vector, right? So every point here is a convex combination of this and this. Okay, so this point here, take a vertex, let's call this the vertex x. So we know that x is equal to a convex combination of this vector and this vector. So for example, it's alpha times 0, 1, 0 plus 1 minus alpha times the vector 0, 0, 1. Okay, so if I make this computation, what I get a vector alpha times 0 is, so the first component will be 0, right, because I have a 0 here and a 0 here. The second component will be alpha, and the third component will be 1 minus alpha, for some alpha between 0 and 1. Okay, so here I have the vector x, so this consists of 0, alpha, 1 minus alpha. And then I have f of x. F of x1, f of x2, f of x3. So one thing that I see immediately from this vector is that the first component is equal to 0. Okay, so in particular, if I look at my colors, here they are. The first component is equal to 0, so f of x1 cannot be smaller than x1, right? This cannot be smaller than 0, right? Because all these numbers are non-negative. So if it's not smaller, if the first component is not smaller than 0, then this color is not red. Okay, so whatever happens here, x is not red. Okay, this is because 0 is smaller or equal to f of x1. Also from point 1 here, I know that every x has a color, right? And if the color is not red, and it has to have a color, so this means that x is green or blue, right? It has either this color or it has this color. So all these here can be, for example, this one is blue, this one is blue, and then maybe the last one here is green. Okay, and I can do a similar thing for the other two boundaries. All right, so in particular, if I take a convex combination of this one and this one, then I see that the second component here is 0, the second component here is 0. So here for all these points here, the second component is 0. Right? So if I look at my colors, in order for me to be able to color it green, I need that f of the second component is smaller than the second component. But if this is already 0, this condition can never hold. Okay? So these here cannot be green. So they have to be either red or blue. For example, let me take this one red, and then maybe the last one blue. Okay, and I can do a similar thing here. Here, if I look at the convex combination between this point and this point, here the last element is 0, here the last element is 0. So here the third component is 0, so all these cannot be blue. Okay, so this indeed shows that all of these vectors cannot be red, all of these vectors cannot be green, and all of these vectors here cannot be blue, and everything is colored. So indeed we have satisfied all the conditions for Sperner's lemma to be applied. Okay, so you can fill in all the other cases in point 3 as we have done before by similar arguments. Okay, so Sperner's lemma tells us, because these conditions, every vertex has a color, these three vertices have different colors, and the sides don't have the color of the opposite peak vertex. Let's say we can apply Sperner's lemma. So there is a small triangle with 3 different colors. Okay, so for example, this one here. I'm not sure that the red one is on top, but that's a possibility, right? So I'm just drawing here a triangle with 3 different colors. It's possible that the red, green, and the blue are on the blue is here, or the green is here, and so on, right? So I'm just drawing a generic triangle. So take this triangle here. So wherever the red is, I will call the red vector R1. Okay, so it's not a component, but this is just a number to indicate this vector. I will call the green G1, and I will call the blue B1. Okay. So what I can do is I can divide all these triangles into smaller triangles, right? So similar as what we have done here, I can always divide this into smaller and smaller and smaller triangles. I can each time find a triangle with 3 different colors. So maybe the first time I have here a big triangle with 3 different colors, and then the second time I will have here a small triangle with 3 different colors, and then maybe here I will have a tiny triangle with 3 different colors. But each time the coloring satisfies the conditions for Sperner's lemma, so I can find a triangle with 3 different colors, right? So take smaller and smaller subdivisions each time. Take a smaller, I can say, triangle with 3 different colors. So I have a, let Rn for the nth subdivision let Rn be the red vertex, and then Gn is the green one, and then Bn is the blue one. Okay, and these triangles get smaller and smaller and smaller, right? So these 3 vertices will get closer and closer and closer together. So in particular, I will have that Rn minus Bn, Rn minus Gn, and then Gn minus Bn. Well, all of these will go to 0. Okay, so that's a given, because the triangles get smaller and smaller, the diameter converges to 0. So all these things will converge to 0. But it's still possible that they move around in this triangle, right? So it's not like they have to be nested inside each other. Okay. So for the red one, I have that the first component of Rn, this is Rn1, is because this has the color red, right? And let me go back to the definition of my colors if I can find them. Okay, the first component of a red vertex is greater or equal to f1 of the first component, right? So this is greater than f of r and 1. For the green vertex, it was the same, but it was for the second component. So Gn2 is greater than f of Gn2. And for the blue one, I have that Bn3 is greater than f of Bn3. Okay, this is because these are red, these are green, and these are blue, and this is the rule of how I colored my vertices. Okay, so Rn, Bn, Gn, these are all sequences in delta 2, right? They don't have to converge, but at least because delta 2 is compact, I know they have a convergent subsequence. And I can make sure that these convergent subsequences coincide. Okay, so I know that there's R phi n that converges to some vector R. I know that B phi n converges to some vector B, and G phi n converges to some vector G. Okay, and R and Bn go to 0, R and Gn goes to 0, the distance between Gn and Bn goes to 0. So similar to what I have done before for the one-dimensional case, I can actually show that all these three here are equal to each other. And let me call this the vector y to be y1, y2, y3. Okay, so similar to before, I have taken a convergent subsequence and then taking the limit, and actually can show that the limits of these sequences, because they get closer and closer together, these sequences, they converge to the same vector. And now I use the same limiting kind of argument as before. So Rn1 is greater than f of R1. This should be along the subsequence R phi n 1, because its red is greater than f R phi n 1. This here converges to the first component of y. This here, because of continuity, converges to f of y 1. And by taking the limits, the inequality changes to weak inequality. The same goes for the green vertices. G phi n2 is bigger than f of g phi n2. This converges to y2. This converges to f of y2, and this becomes a weak inequality. And then b phi n3 is bigger than f of b phi n3. B converges to y3, b phi n3 converges to y3. Because of continuity of f, this converges to f of y, the third component, and then this weak inequality becomes a weak inequality. Okay, so we have y1, y2, y3. This is greater or equal to f of y1. This is greater or equal to f of y2. This is greater or equal to f of y3. We have three numbers that add up to 1. Here we have three numbers that add up to 1. Okay, they're all non-negative. So all these weak inequalities have to be equalities, because otherwise you would have a strict inequality here. So again, this implies that y is equal to f of y. So y is a fixed point. Okay, and because here we are dealing with a compact set, we know that the limit is in delta 2. So y is a fixed point, it's in delta 2. So this should be a contradiction, because at the very beginning, yes, here it is, we assume that there was no fixed point. Okay, so this is the desired contradiction that you wanted to show. So the proof is very similar to the one-dimensional case. So the only thing that's a bit different is how we can show that these boundary nodes don't have the color of the opposite extreme vertex, right? And this uses the complex combination of these two to show that one element is 0, so it cannot have a color of the opposite side. Okay, so this was the proof of Brouwer's fixed point theorem for delta 1 and delta 2. And then we can knead these sets delta 1 and delta 2 into other shapes by continuous transformations, and then the fixed point result still holds for continuous functions on these reshaped domains, should I say. Okay, thank you for watching.